So this is the third and the last part of the three-part series of lectures on reasoning under uncertainty. What we are going to do in today's class is to go over a few other types of reasoning under uncertainty, other types of logics, other types of methods for handling uncertainty, and conclude with a set of research directions which are gaining significance in recent times. To start with, I am going to recap a little bit on a particular problem that we started discussing in the previous class, namely one of the ways to handle inference in multiply connected belief networks, that is belief networks which are not polytrees, is to do what is called stochastic simulation. So essentially what this means is that we choose a large number of samples or sample data set, and from that data set we try to estimate the values of the probabilities. But one of the problems that arises when we do this kind of a sampling is what is called statistical bias. So we are going to take a look at a very famous paradox called Simpson's paradox, which kind of nicely demonstrates the effect of sampling and the corresponding bias that may give an incorrect impression about the probabilities. So it's about a problem, it has been actually cast in many different subject domains, but let's look at the problem from the original setting, where we try to deduce whether a particular new drug will be approved by the drug authorities or not. That is, should the drug be administered on patients or not. So when the sample was when sample experiments were conducted, this is what was found for all the male patients. It was found that of the people who were administered the drug, 18 people recovered and 12 did not recover. So the recovery rate for those who were given the drug was 60%, whereas for those who were not given the drug, there were 7 recovered people and 3 people did not recover. So the recovery rate was 70%. Now, as you can see that the recovery rate, as is shown by this experiment, the recovery rate for those who were not given the drug actually turns out to be higher. So given this evidence, it appears that not giving the drug is the better option, because the recovery rate is higher when a person is not given the drug as opposed to when given the drug. Likewise, when we look at the statistics for the females who were administered the drug, we find 2 of them recovered and 8 did not recover. So the recovery rate is actually quite poor, that's 20%. And for those who are not given the drug, 9 people recovered and 21 did not recover. So that gives us 30% recovery rate for those who are not given drugs. Now what happens when we add these up? When we add up these numbers, then you can see that 18 men and 2 women were given the drug, so 20 people received the drug, and we can see that 12 males recovered and 8 females recovered, so 20 people recovered and 20 people did not recover. So the recovery rate turns out to be 50%. Again, when we look at the ones who were not given the drug, so we find that 16 people recovered and 24 people did not recover, so the recovery rate is 40%. So in spite of the fact that when we looked at the males in isolation and the females in isolation, in both of these cases we found that the recovery rate for not being given the drug is higher than that for patients who are given the drug. When I combine them, I find that the recovery rate for those who are given the drug is now higher than those who are not given the drug. So this is where we have the paradox. So what exactly is happening here? Should the drug be administered or not? So if you look at the samples very carefully, you will notice that the recovery rate in the case of females for those who are given the drug is actually very low, that is 20%. Now the ones who are not given the drug, for females again it's 30%, whereas for the males who are not given the drug, the recovery rate is 70%. Now the number of females who were selected in this study, does it equal the number of males? So let's see. If I add up the four numbers that you get in the table corresponding to males, then you get 18 plus 12, which is 30, and then 10, which is 40. For the females, what you see is you get 21 plus 10, which is 31, plus 9, 40. So the total number of males and the total number of females in the study are equal. But if you look at the number of people who received the drug, then for the males it's 18 plus 12, that is 30 people received the drug. For the females, only 10 people were given the drug. So that's where the bias is coming in. The drug was administered on too few females, and as you know that in females the recovery rate is very poor for the drug. So by selecting fewer females for administering the drug, we are kind of biasing the experiment, and thereby we end up with this kind of a finding that the recovery rate for those who are given the drug is actually higher than those who were not given the drug. So if you look at the problem here in terms of the Bayesian probabilistic analysis, the probability of recovery given that a person is male and given the drug is 0.6, which is the first row, the 60%. And the probability of recovery given that a person is female and is administered the drug is 0.2, which is the first row corresponding to the table for the females. And now if I want to find out the probability of recovery given the drug, then I get two terms. The first term is that probability of recovery given male and given drug times probability of given drug given that the person is male. So here is where we find the bias coming in. So let me bring this up into full screen. So the bias is coming in here, that the probability that you are given the drug if you are male is actually 30 out of 40. So that is a healthy figure, whereas this probability is 10 out of 40. So that is a much smaller figure as compared to this. So this is where the sampling bias is coming in, thereby we get a incorrect deduction. So now when we talk about reasoning in the probabilistic sense, if we do it based on sampling, obviously we will have to make sure that the samples are chosen in a way that no kind of bias creeps into the experiments. Now, reasoning with uncertainty has been factored into many types of reasoning systems, particularly some of the expert systems that we are going to talk about. They use probabilistic rules, and also facts are associated with probabilities. One of the types of reasoning which has been quite popular is called default reasoning. So some conclusions are made by default unless a counter evidence is obtained, and therefore if I assume something by default, then the reasoning becomes non-monotonic, because then after some time I might find that some of my assumptions were incorrect, and if I have deduced things using those assumptions, then those deductions are also then incorrect. Now this is one of the problems in non-monotonic reasoning. And when we do probabilistic reasoning, then unless we know exactly the probabilities of certain variables, if we leave that open, then we may need to change the values of the probabilities as new evidence appears. So when I don't know about some variables, then I may reach certain probabilities for certain facts or certain attributes, but then if I later on my knowledge is enhanced by some more evidence, then I may have to go back and change those probabilities. So in a way, this is non-monotonic reasoning, because the probability values will change because of my increased knowledge about certain facts and rules. A few issues that appear in rule-based methods for uncertain reasoning are locality. So in logical reasoning systems, if we have A implies B, then we can conclude B given evidence about A without worrying about any other rules. In probabilistic systems, we need to consider all the available evidence. For detachment, once a logical proof is found for proposition B, we can use it regardless of how it was derived. That is, it can be detached from its justification. In probabilistic reasoning, the source of the evidence is important for subsequent reasoning. This is something that we have observed when we were dealing with the belief networks. Then we look at truth functionality. In logic, the truth of complex sentences can be computed from the truth of the components. Probability combination does not work this way except under very strong independent assumptions. So one of the early and very well studied truth functional system for uncertain reasoning is the certainty factors model, which was developed for a medical diagnostic program called MyScene. What MyScene does is basically it acts as an expert system for pathological diagnosis. So you have probabilistic rules depending on the set of tested parameters, and from that, with certain probability, you can infer about the medical conditions as may be inferred from the pathological studies. Now, one of the things which comes up and is very closely related to the probability theory that we have studied is a thing called belief. So Dempster-Shafer theory is one of the theories which talks about this. It creates a distinction between uncertainty and ignorance. So uncertainty may be statistical, it may be because I have a probabilistic value for something, but ignorance is something else. So let us understand what is this different. So we use something called a belief function. So let us say BELX is the probability that the evidence supports the proposition. So let's take an example. So in this theory, when we do not have any evidence about x, we assign the belief of x to be 0 as well as the belief of not x to be 0. So it's like if I do not have any evidence about the structure of a person and I am asked to determine whether the person is fat or not, then I really don't know anything about that person. So my belief that the person is fat is 0 and my belief that the person is not fat is also 0. Now this is not something that you will see in probabilistic reasoning. In the traditional Bayesian system, for a variable, if the probability of x is 0, then the probability of not x will be 1. Now let's take an example to understand what this theory is actually trying to do that is different from the Bayesian probabilistic analysis. So if we do not know whether a coin is fair, then my belief that a toss of the coin will come up with heads and my belief that the coin will come up with tails are both 0, because I really don't know whether the coin is fair or biased or whatever. Since I do not know that, I should not assume that it is fair and then say that the probability of heads is 0.5 and the probability of not heads is 0.5. That we should not do, because we do not know the nature of the coin. Now suppose we are given that the coin is fair with 90% certainty. That is, it is fair, but it's kind of biased towards the heads with some 90% probability. If we know that, then I can say that the belief that heads will come up is 0.9 into 0.5 and belief that not heads will come up is also 0.9 into 0.5. Now see what's happening here. If we knew that the coin is 100% fair, then we would actually have the belief of heads would be 0.5 and the belief of not heads would be 0.5. But because I do not know here whether the coin is fair or not, that is, I know it is probably fair with a probability of 90%, then I can say that my belief for heads is 0.45 and the belief for not heads is also 0.45. And if you add up 0.45 and 0.45, you get 0.9, and then there is a gap of 0.1 which is not accounted for by the evidence. That is, we really do not know with 100% certainty that the coin is fair. So this is what Dempster-Shafer theory proposed, and to the best of my knowledge, it has not really been used in too many systems. Rather, there is another form of reasoning which is very closely related to probabilistic reasoning, but actually is not probabilistic reasoning, is a type of logic called fuzzy logic. Now let's first understand what's the difference between probabilistic logic and fuzzy logic. So fuzzy logic or fuzzy set theory is a means of specifying how well an object satisfies a vague description. So here, as opposed to the Bayesian probabilistic analysis, where a truth of a variable can either be true or false, that is, the truth is either 0 or 1, here we can have a graded truth. And here it is not about lack of knowledge, it is more about the degree of truth as we would like to state it. So for example, suppose we are told that 40% of Indians are obese, right? Now if you know that 40% of Indians are obese, and I tell you that, well, X is an Indian, and you cannot see X, you have never met X, you cannot see X, but you are told that X is an Indian, and you are told that 40% of Indians are obese, then you may say that the probability that X is obese is 0.4 and the probability that X is not obese is 0.6. Now that comes automatically from the knowledge that 40% of Indians are obese. But it's an uncertain reasoning because I have not seen the person X, so I am just going by the probability that because the person is Indian, so the probability that X is obese given that X is Indian is 0.4. Now as opposed to that, now think of a situation where you can see the person. So the person is here with us and we can see his dimensions, of course, and now we ask, is this person fat? Now when we talk about fuzzy logic, we ask how fat. So fat or obesity is not a Boolean attribute. It is an attribute which has a graded value. So somebody might be very obese, so I will say that the truth of the fact that X is obese is 0.9 because the person is really very obese, and there may be a mildly obese person, maybe the truth value of that person being obese is 0.4. So here, as opposed to probability, we have a graded truth, and we build a set of rules around this graded truth. So for example, if A and B are two fuzzy variables, then the conjunction, the truth of the conjunction of A and B is the minimum of the truth of A and the truth of B. We are going to use this in a short while from now through an example. So and of the truths is expressed by min of the truths of the individual variables. Likewise, the truth of A or B is defined as the max of the truth of A and the truth of B. Remember that in fuzzy logic, the truth of A and the truth of B can be any number, any real number between 0 and 1. And the truth of not A is 1 minus truth of A. So for example, if I say that the truth that this person is fat is 0.8, then the truth that this person is not fat is 0.2. Okay. Now let's see an example to understand how fuzzy reasoning works. We are not going to go into more details in this class because that would kind of take us away from the main goal of this course. So we are going to just do this one example to get an understanding of how we do fuzzy reasoning. So we discussed the problem of cardiac health management, and we are given a set of rules and we are given some facts. So the rules, as you can see here, are the following. The first rule says diet is low and exercise is high implies balance. That is, I am trying to define what is a balanced diet, and I am saying that if the diet is low and the exercise is high, then the person is in a balanced state. And if diet is high or exercise is low, then the person is in an unbalanced state. In a balanced state, the risk of a cardiac complication is low. In an unbalanced state, the risk of a cardiac complication is high. For a person, it is given that, so this part that we saw so far the part that we saw so far are the set of rules. That is, these are my set of rules, fuzzy rules. I'm going to come in a moment to describe why these are fuzzy. I mean, they look at as normal rules here, but the analysis that we will do will show that where fuzzy logic comes in. And this is what we are given. We are given that for a particular person, the person has a 3000 calories per day diet, and the person burns 1000 calories per day. And now we want to ask that what is the risk of cardiac disease for this person. Now, at the heart of fuzzy logic are what are called membership functions. So let me write down. Membership functions. And what does membership functions tell us? It tells us the truth of a variable in terms of a function of certain parameters regarding the variable. So my membership function may be something like this, or as we shall see, there can be many different types of membership functions. So let us go ahead with the example. So here is a couple of membership functions that we are given here. Let's look at the first membership function on the left. What it tells us is that as a function of, just give me a moment, I seem to have lost my mouse. Yes, so I have calories consumed here, and I have as a function of calories consumed my membership for the truth of the proposition diet high. What does this mean? It means that if I look at a particular calorie intake, let's say if I look at 3000 calories, which I think was the intake for the diet of the person that we are talking about, then I will say that the person has a membership of 0.6 for the proposition diet high. So what does that mean? That diet high is for this person, diet high is true with a truth value, that is T of diet height, the truth value of diet high for the calorie consumption of 3000 turns out to be 0.6. So that's what a membership function gives us. It gives us, corresponding to the number of calories consumed, what is the truth for diet high. Now, diet low is just the negation of diet high. So if you remember what we mentioned just now, that the truth of not of A is 1 minus the truth of A. So that's why we get this other curve. So for diet high, the function that is shown here follows this equation, and for the diet low it is just 1 minus that. Okay. So now what we do is that when we fit in the value of the calories that calorie intake for the person, I get the membership for diet high as 0.6 and the membership for diet low is 0.4. You can see that the membership for diet low is 0.4 by just looking at this point there. Okay, so that's about finding out the membership for diet high and diet low. So these are the truth values, if you may call it, for diet high and diet low. And then we do the same thing for exercise, where I am given the membership function for exercise high and the membership function for exercise low, and I find that for a daily calorie burned of 1000, which is what we were given, remember that the person burns 1000 calories every day, then the membership for exercise high is then 1000 by 2000, which is coming to 0.5. How do we get that 1000 by 2000? So we go up this curve, and then when we go and find out what is the membership for that, we find it's 0.5. Okay, and similarly membership for exercise low is 0.5. Now we come to the rules. Now what we found out from the previous slide, that my truth for diet high is 0.6, truth for exercise high is 0.5. We also found out that the truth for diet low is 0.4, truth for exercise low is 0.5. Now let's take the first rule, which says that if diet is low here and exercise is high, then we can say that the person is balanced. So the truth of balanced here is computed as here we have and, you see, and in fuzzy logic and is mean. So therefore I take the truth of diet low, and what was the truth of diet low? It is 0.4, and then I take the truth of exercise high. The truth of exercise high is 0.5. So I take the mean of the two, because this is and, so I take the mean of the two, and therefore I get 0.4 as the membership value for truth balance, for the balanced. For the proposition balanced, my truth is 0.4. When I look at the truth of unbalanced, then I can simply do truth of 1 minus truth of balance, so I get that as 0.6. Okay. The other way to do that would be to take the negation, or if I go by this one, if I go by this rule, it says diet is high or exercise is low. So because this is or, so we will take the max as per fuzzy logic, and then I take the truth of diet high, which is 0.6, and that of exercise low, which is 0.5, and then take the maximum of the two to get this value of 0.6. Then I look at the rule which says balanced implies risk is low. Now we found out that the truth of balanced is 0.4, so we can say that the truth of risk is low is 0.4. Similarly, we looked at the truth of unbalanced as 0.6, so the truth of risk is high is also 0.6. Now we have found out that the truth of risk is low, it has the fuzzy membership of 0.4, and the truth of risk is high has a fuzzy membership of 0.6. Now to translate this back into the actual probability that the person will have a cardiac problem, we need again a translation from the membership values of risk is low and the membership values of risk is high to the actual percentages of probability that the person will have a cardiac problem. So what we then do is look at these membership functions. These membership functions are now required to interpret the output that we got from the fuzzy analysis. The fuzzy analysis told us that the truth value for high risk is 0.6 for this patient. Now what we do now is we say that, well, the truth value of the patient for high risk is 0.6, so I can actually think of that as a straight line like this. But I am given that the actual likelihood of heart disease, which is here, which is the x-axis, the actual likelihood of heart disease varies with the membership for the risk high as per this curve, So now I need to see the intersection of these two, and then you know that in fuzzy logic the intersection is the mean of the two. So if I take the mean of these two curves, that is this one and this one, at all points, then I get this one. So this is the curve corresponding to this patient and the likelihood of the person having a heart disease. Now we look at the other factor, namely risk low. Now if you look at this one goes, the membership function for risk high goes up to 0.8, that is, this is the maximum that you see. So now it is going to be that will therefore be nothing but 0.8 minus this thing. So whatever curve that you saw in the previous slide, this is 0.8 minus that, so you get a curve like this. And I did find through my fuzzy analysis that the truth of risk low is 0.4. So what do I do here? I come to this 0.4, and then that is for my patient. This is my truth for the membership value for risk low. Now again, if we take the mean of the two, then we get this curve, the second curve. This one, right? Now we want to put things together. What we do is we take the aggregated risk function. So we have the fuzzy values for the high risk, that is this curve, and then you have this for the risk low. Now what you do is take the OR of the two, that is the union of the two, to get the aggregated risk, which then becomes this curve. So as you can see that up to this point it follows the lower curve, and then from that point, that was where 50, I think, from there this part comes here. And now I want to find out that for this membership function for this particular patient, what is the risk that the person will have a heart disease. So to do that, what we need to do is to find out the area under this curve, and that we get by integrating the curve at these three segments, and by that we get a total value of 47.5, and then by that we conclude that the likelihood of heart disease for this person is 47.5%. So this was a very quick example on the use of fuzzy logic for carrying out a probabilistic deduction. I am sure you will have many questions. We will take them during the online sessions. Please go through the slides, please go through the lecture, and whatever doubts you may have will be taken up during the online session. So to conclude this particular lecture, let us think of what are the other things that we did not do in this particular set of 3 lectures. So firstly, probabilistic reasoning is an integral part of many domains of AI, and we intend to study the following in future when we go over topics like reinforcement learning. We will learn about probabilistic reasoning in state machines. That is, you have things like Markov chains and Markov decision processes where you have a temporal behavior, that is, an agent may move from one state to another, and these graphs which model the state machines will also have loops, so they are ideal for modeling recurrent behavior. And we shall see that there are machine learning algorithms like reinforcement learning which work with the underlying Markov decision processes. This is the part that we will take up later. Here are a few other things that I would like to point out, some of the things where probabilistic reasoning is being used, and they have a lot of promise not only in machine learning but in other forms of AI. So one area is Bayesian optimization, which is an advanced method for problem solving under limited knowledge of the state space. So if you do not know, so there is a difference again between lack of knowledge which may be gained through further exploration, as you know, as you did for example in heuristic search. Initially you know very little about the state space, but as you keep on expanding the state space, you generate new nodes, you apply heuristic functions on them, and then you come to know about that. Now in an optimization state space like you saw in A star, we can use techniques like Bayesian optimization to fill us knowledge about those parts of the state space where our knowledge is limited. And the more you get informed about the parts of the state space which are not within your knowledge, you will have a better way of optimizing the overall cost function. Bayesian learning methods are gaining in popularity for making classifiers. They are becoming more important because uncertainty needs to be factored into classifiers so that the classifier can separate out lack of knowledge as one of the outcomes. So you may remember that in the first lecture I talked about developing a classifier which can separate out wolves from huskies, and we discussed that in the absence of any explainable model for machine learning, we stand the risk of learning a classifier which kind of separates wolves from huskies by using a completely different type of entity, like whether there is snow in the background. So we discussed that thing. But suppose you are asked to design a classifier for separating wolves from huskies, and after you have trained the classifier, you present it with the picture of a cat. Now a standard classifier will try to see whether the cat looks more like a wolf or more like a husky, and it will definitely bin it as one of them. But what we need is a classifier which should have the ability to say that, well, for this picture I don't know, it doesn't seem like a wolf, it doesn't seem like a husky, and it doesn't seem like anything that I've seen in the past, so this is something which I don't know. How do we bring in this don't know, the lack of knowledge or the uncertainty into classification? So that is an interesting area, and it is coming up in many different ways, not only for classifiers but other forms of machine learning as well. One of the interesting areas for explainable AI or explainable ways of learning things is a structure called stochastic AND/OR graphs. As you know, AND/OR graphs have both types of nodes. There are AND nodes and OR nodes, and in an OR node you have to select any one of your children. In an AND node you have to select all of the children, and there are many different types of objects which can be described in terms of AND/OR graphs. For example, if you talk about a clock, for example, a clock has a dial, it has hands, and it has markings, the markings which tell you whether it's 12 o'clock or 1 o'clock or 2 o'clock, etc. Now there are many different varieties of clock. So for example, you may have a round dial clock, you may have a square dial clock, you may have a clock with a pendulum, you may have a clock without a pendulum. So these are my OR choices. Now within a choice, suppose I take a round dialed clock, then within that I may have further artifacts, like I may have 2 hands, I may have 3 hands, and these days you also get watches which has only 1 hand, and then that becomes again another type of OR. And then for a clock I know that I have to have hands and I have to have dials, so there is an AND out there. Now when there is a object whose structure is not known a priori, then from the data, if I want to construct an AND/OR graph, then I will need a stochastic method of doing it, because I will not get universal data, so I will have to rely on limited amount of data, and based on that I may have to deduce that what is the structure of the object which I am trying to recognize. So stochastic AND/OR graphs is an interesting way of automatically learning that, and it uses probability and it uses the structure of AND/OR graphs. So there are many different offshoots of probabilistic reasoning, which I am afraid we don't have the scope of covering in this course. We will work out several examples and several problems on the topics that we have covered in the online classes, and I strongly encourage you to look at some of these new things where probability is getting factored into classical AI, and also in this combination making good impact in modern AI by combining ML and these types of classical reasoning. So I hope you enjoyed the topic, and thank you very much for your attention.